we take another example, and this example, we are looking for limits as x, y approaches 0, 0, x4 plus 2x squared plus 2y squared plus y4 all over x squared plus y squared. By the accumulation point theorem, we check limits along y is equal to 0. Now if y is 0, in place of all y's, I put what? 0, and it becomes only a function of x. So I write limit as x approaches 0, x4 plus 2x squared all over x squared. Now, when we factorize 2 out from the top and from the down, they will cancel out nicely. Okay, and this will have limit as x approaches 0, x2 plus 2. We'll have this, okay, because the down will have cancelled. And when we allow x to go to 0, this will give us 2. Good. Now we check again limit along x is equal to 0. Now along x is equal to 0, then we will have limit as y approaches 0. In place of x, we put 0, and we'll have 2y squared plus y4 all over y squared. Like this one at the top, factorize y squared outside, right? From the top and from the down, and we'll cancel out. And we'll have limit as y approaches 0, y squared, or 2 plus y squared, right? So 2 plus y squared, which is equal to 2. Okay. Now we check along the line y is equal to x. Now along y is equal to x, then we'll have limit as in place of y we put x. So as x goes to 0, I will have x4 plus 2x squared plus 2x squared plus plus x4 all over x squared plus x squared. And it will reduce to become limit as x approaches 0. I'll have 2 of them, 4 of these, and 2 of that. So I'm going to have 4x squared plus 2x4 all over 2x squared. 2x squared. Let me just clean the top and proceed. Okay, now, good. Let me repeat. From here, we can factorize 2x squared out from the top and down to cancel out. And I'll have limits as x approaches 0, 2 plus x squared. When we allow x to go to 0, this one will give us what? 0. Next, we find limits along the line y is equal to x squared. Of course, y is equal to x squared also passes through the point 0, 0. So along y is equal to x squared, we are going to have limits as x approaches 0, x4 plus 2x squared plus 2x4 plus x8 all over x squared plus x4. And here we can factorize x squared from the top, from the bottom, and you cancel, and it becomes limit as x approaches 0, x squared plus 2 plus, oh, okay, let me just sum this one up. Let me just add this to it so that I have 6 of them, right? So when 2 goes out, I'll have, oh, I have 3 of them. So I have 3 of these, right? Okay, so 3x squared plus 2 plus x to the power 6 all over 1 plus x to the power 2. And here, if we allow x to go to 0, if we allow x to go to 0, this will go to 0, this will go to 0, this will go to 0, and I'll have 2 over 1. So this is equal to 2. Okay, now somebody will ask, in our checking, when do we stop? In our checking, when do we stop? Okay, for me, I always check around 4 or 5 lines. And if I get the same answer, then I'll use what I call epsilon delta to verify. You would agree with me that there are lots of lines that pass to the point 0, 0, and I can't check for all of them. So I just pick like 4 or 5 or maybe 6. When I check and I'm getting the same answer, I can't even conclude that the limit exists, and in this case, the limit is 2. I can't conclude. From the accumulation point theory, it looks like the limit is what? 2. But we can't conclude unless we use the epsilon delta definition to verify that actually the limit exists and the limit is 2. So let's look at how to use the epsilon delta definition to verify. Now, we are claiming that if the limit exists and the limit is 2, then for epsilon greater than 0, there exists some delta of epsilon also greater than 0, such that whenever the distance between P and A is between 0 and delta, whenever this is true, then f of P minus A absolute is less than epsilon. Now let's see clearly. Let's define some things here. For the definition, clearly my point P is equal to the point xy, and my point A is 0, 0. And here f of P is the same as f of xy, which is x4 plus x squared is 2x squared, right? S4 plus 2x squared plus 2x squared plus 2y squared plus y4 all over x squared plus y squared. So we have, I think, everything we need. Now we know our P, we know our A, we know f of P, yep, which is f of xy. We know all that. Good. Now let's begin by the distance between the point P and A. Remember, P is xy, so the distance between x, y, and the point 0, 0 clearly is just the square root of x squared plus y squared. Now we claim that the square root of x squared plus y squared is between 0 and delta. What we can also learn from this is that for every point x, y, x will definitely be less or equal to the square root of x squared plus y squared, and y will also be definitely less or equal to the square root of x squared plus y squared. Or better still, this is bigger than that and this is also bigger than that. It works in all cases. Okay, good. I'm running out of time. Let me see. I'll still take my time, eh? No sweat. Yeah. I'll still take my time. Let's see. We can see this is becoming clumsy, but it will come out fine. If you copy this thing down, let me clean the board. Okay, now this is where I start from. I start from where it says that f of p minus l is less than epsilon. F of p is that x squared plus, let me use f of xy. F of xy minus l, which is 2. Here l is what we are claiming our limit is, right? So x4 plus 2x squared plus 2y squared plus y4 all over s squared plus y squared minus 2 absolute that should be less than epsilon. Okay, should be less than epsilon. Now when we find LCM here, this one goes to multiply that and it will cancel out the top nicely. You can take it step by step, right? We'll get f4 plus y4 all over x squared plus y squared, that less than epsilon. Okay, now next, in place of x squared, x, you know, the down part here looks like our delta, right? Remember, we claimed that the distance between our point x, y, and 0, 0, which we claim is the square root of x squared plus y squared, should be between its distance, so it's always positive, right? Should be between 0 and delta, right? Okay, so all right, let me stop here.